Good afternoon, everyone. I'm very excited to be here on this trip and on this tour and participate in this summer camp. It's a great initiative to bring transport scientists and lecturers from around the world to share some ideas and to hopefully build common grounds for collaboration going forward in research, in teaching, and even in business. So very happy to be here and glad to start the first lecture of this program this year. I prepared 2 lectures for today, and I intentionally tried to keep a balance between what's really interesting from industry-facing research and what's also interesting from theoretical academic research. Over the past few years, I've been involved in a lot of industry-facing practical research. And the first lecture is going to talk a little bit about one of these projects. But in these projects, we also, because we are an academic entity, we need to keep the balance between what industry partners want from us versus what we can publish in scientific journals. So it's not just the practical, proven, and standard techniques that industry likes to see. It has to be novel and innovative and new methods as well for us to be able to publish. So first lecture is going to be dealing more with industry-facing research, what brings us money, what brings us data, what brings us partners. Second lecture is more theoretical and more modeling. So that's a little bit of context about my lectures today. So the first lecture is dealing with telematics data, vehicle telematics data and its application in traffic management for safety of operation and efficiency of operation. Little bit of background about myself. I'm originally from Iran, right now based in Melbourne, a proud Australian citizen, but I lived in the US and worked in the US for many years as well. So I worked in government in the US, San Francisco County Transportation Authority. I did my PhD in University of Arizona. I did a postdoc at MIT, and I also did a postdoc at University of Queensland before I landed my University of Melbourne job now. My research mainly deals with big data in transport. I'm most interested in big data in public transport and big data in traffic systems. So I have a lot of research kind of interest in public transport, big data, the data that comes from fare collection systems, smart cards, for example, and also data that comes from vehicles, the traffic data on the other side. So my PhD was in optimization of traffic for large networks during disasters and for evacuation. So that involves advisory information, how you can basically identify the best routes for traffic to evacuate the network, and also how you can optimize the signal timing to accommodate the most efficient evacuation. So the first presentation will deal with an iMove project. iMove is a collaborative research center that brings academia and government on the same table in Australia. So in this particular project, which is dealing with connected telematics data for traffic efficiency, we have 4 state governments that funded a project for over $1 million. We have all the important states in Australia supporting us, sitting us on the same table, and asking us research questions. And we wrote this proposal in conjunction with them. And we are conducting the research and delivering the outcomes regularly to these industry stakeholders as well. So I have a big team of researchers that work with me on this project. Most of them are PhD students that are basically, in addition to their scholarship, they get paid for participating in these research projects with us. This is also a good opportunity to advertise. If you're doing a master's, for example, degree, or even if you're doing a PhD, and if you're interested to work with us, come to Melbourne and get involved in our research. There's opportunity, especially if you're interested in doing a PhD with us. So please stay in contact if you're interested. So this is a team. All the credit goes to my team who have done amazing work in this research project. And I'm going to talk about some of the major findings. So we wrote 100+ pages of report in this project. I'm going to talk about major and most important findings from this project. If you're interested, I can share with you the report of the project as well. The idea in this project was to investigate vehicle location information and use this data that can come from new vehicles, basically. New vehicles that have a SIM card on them. Many vehicles nowadays do actually have a SIM card without us knowing and communicate their location and some basic information to the manufacturer. Usually the user of the vehicle doesn't really interfere with that system at all. But that data is available, and the idea in this project was for government, basically. 4 state governments were interested to know what can they do if this data is available to them in almost real time, and how can they use it for improving the efficiency of transport and improving the safety on the roads. So the idea is basically using the low-hanging fruit here. So this is one component of connectivity. You may all be familiar with connectivity when vehicles may actually have a communication device. They may communicate with vehicles in the vicinity. They may communicate with the infrastructure, with the traffic signal, and they may be connected to the network. But we do research in utilizing these communication kind of opportunities as well. But this project is not dealing with that. This project is dealing with low-hanging fruit of connectivity, just vehicle location information. That information may come from an array of different industries. It can be connected vehicles. It can be, for example, coming from telecommunication industry that provides the mobile kind of antenna. It can come from telematics. It can come from even from Uber-type systems, taxi systems, delivery systems. So any industry that kind of has data on vehicle locations, and it doesn't have to be cars. It can be public transport. It can be smart mobility and micro-mobility like scooters, bicycles, electric bikes. How can we use this data to improve the efficiency? So that's why I call it low-hanging fruit of connectivity, because it's almost the common denominator of all new vehicles that is out there. It doesn't necessarily require a two-way or one-way communication. It's just as long as we have the GPS information, we want to know what can we do with this type information. So one of the most important data sets that we explored, and majority of my presentation is based on this data set, is a new startup company called Compass IoT that does aggregate data from different car manufacturing companies. For example, new Hyundai, new Kia, new BMW, new Mercedes. All these vehicles do actually share their information, the location, with the central. For example, if your car gets stolen, you can actually know where it's located, basically. So a company like Compass IoT, there are many alternatives of this in different countries, do aggregate data from different sources and process the data and share it for different applications with research centers and with even private businesses as well. So the data that is available to us is from the entire state of Victoria, which is basically the the state where Melbourne is in, is the capital. And we had the data for an entire year for a subset of vehicles that are present in Compass IoT. I'll talk about the penetration rate and about size of the data in a bit. But what's really interesting about this data is that not only we have the GPS locations and speed and acceleration and deceleration, we also have some gyroscopic information as well. So when the vehicle falls in a pothole, for example, or loses control, or loses friction, an event is registered, and that event is also recorded. So when a vehicle is registering, for example, a roll motion, or a yaw motion, or a pitch motion, that's also recorded in the data set. And that's very valuable because it basically gives us clear indication where there are some safety risks to the vehicle and may need a little bit more attention. So in addition to acceleration, we have gyroscopic information in the data as well. The type of use cases that our industry partners were interested in are basically classified in 4 major directions. So traffic delay reduction at signalized intersection. How can we operate the traffic signal light more effectively and more efficiently using this type data? And then multimodality of operation. This is taking into account that there are all modes, different modes of transport utilizing the road. It's not just cars. If we only operate the traffic signals for priority for cars, we are basically providing priority for cars and enforcing the negative cycle of car dependency and car investments on the road. Instead, what we are proposing and what we are testing in this project is to, for example, take into account public transport priority, count and predict number of people that are on board the tram or bus when it comes to intersection, count the number of people or predict number of people that may be waiting downstream for that bus when the bus is stuck in traffic, when the bus is stuck in traffic signal, and take all of those consideration into the calculation when we optimize the signal timing at the intersection. So it's not just counting the number of vehicles and trying to optimize the green time for vehicles, but taking into account number of pedestrians, number of passengers on board public transport, number of cyclists, so on and so forth. So that's the multimodality of operation that we advocate very strongly and we investigate in our research as well. The other dimension is traffic safety and operational intervention, identifying where traffic safety risk may actually be present and how we can address that using the operational measures. Like, is it possible to control, for example, the speed limit and reduce the traffic risk? Is it possible to operate traffic signals differently to make sure that the speed profile is more smooth, vehicles do not have to stop and go as much to reduce the risk, and all opportunities in that space as well. The last dimension of our use cases is dealing with reporting and insights. This is very important for government. They want to know how they're operating their roads. They want to know, for example, if they conduct a project, if they change the geometric design of a particular intersection, they want to know what happened before and after. How did they basically affect the speed on the road? How was the safety performance before and after? And so on and so forth. So reporting is basically very important application, and we wanted to know what is it that we can extract from this type data. So these are basically generally 4 major dimensions of use cases that we tested. Any questions so far? All good? All right. So we just released an interim report for the project and basically reported 3 major clusters of findings. So the first cluster of finding is dealing with implications for traffic monitoring and understanding what's going on our roads. The second one is dealing with intersection management and signal optimization. And the last one is dealing with implications for road safety. So I'll start with the first one. For every cluster, I briefly mentioned some of the major highlights, and then I'll talk a little bit more in details about each one. So the first important thing is that we are observing an increasing adoption of these new vehicles on our road. So it's very safe to assume that sooner or later we will have an entire fleet that is broadcasting their location and their speed and their acceleration and deceleration. So we should be prepared to use that data. And this data is very rich. It's not just for operational measures, for example, speed management or traffic signal, but it can also be used for planning applications. For example, it is a rich data set that tells us where people basically go and where do they come from, which path do they take, and how frequent do they make these trips. All of these decisions, you may all be familiar with 4-step travel demand forecasting, strategic modeling. How many of you have seen and are familiar with 4-step travel demand forecasting? With raise of hand, please show. Yep. Good, good. So in those models, we try to predict and model how many trips are going to be made in the network, how many trips are produced in each and every zone, and how many trips are going from every zone to every zone by every specific mode. This data is going to be game changer for that, because instead of trying to guess, instead of trying to develop complicated models, we would get good indication of actual data, actual observation. I'll talk about a paradigm shift from a model-heavy research in transport science to a data-heavy and data-rich type of research in transport. We'll talk about that a little bit, but the first observation here is that we are observing an increasing adoption rate. It's likely to assume that every vehicle is going to broadcast their information probably in 10, 15 years. As soon as older cars are kind of retiring from the fleet and new cars are replacing them, we are likely to assume this data is available. However, one interesting observation that we made was this starts with richer suburbs first. So those suburbs that have higher salaries and higher average income would start to display more vehicles from this type. And that introduces a bias. For example, if you are using this data for traffic signal optimization, you will be, and if you're not aware of this bias, you may be favoring richer population versus poorer population. And that's an equity issue that you may be aware of as a transport engineer, for example. So that bias is interesting, and I'll talk about that in a bit as well. What was also reported as one of the very interesting findings was this data when it's combined with the existing data. So you will see, I'll talk about penetration rate, something about 5% is what we have. So out of 100 vehicles that are entering every street, for example, on average in Melbourne, 5 of them maximum would actually be recorded in this data. We're talking about 95 vehicles or so that are going under the radar. However, this count is recorded at our intersection using the loop detectors at the intersection. So what we explored here was we fused this data with the data from loop detectors that count the actual number of vehicles and produced the trajectory information. So majority of value in this data comes from this fusion, and we'll talk about that fusion in a bit. The other finding was speed analysis. So we looked at the speed profiles at the intersections for different type of movements. For example, for through movements, for left turn, for right turns, we looked at the speed profiles and we realized that there are many vehicles that are speeding, that are actually making left and right turns and endangering pedestrians at intersections with really high speeds. So that's a very important kind of finding the data that doesn't really exist using any types of sensors on our roads. The last but not least was observation about heavy vehicles. Something about 5% of data comes from trucks and delivery vans. And they do actually display very interesting patterns of speed, acceleration, and deceleration. Truck drivers are a lot more experienced than average passenger car driver. So their acceleration and deceleration information is actually very different and can actually be detected from the data as well. So this figure shows the penetration rate on about 10 of our major streets in Melbourne. Name of these streets may be familiar to you if you visited Melbourne or if you lived in Melbourne. So as you can see, the penetration rates starting from something about like the start of 2022 all the way to end of 2022. The data is from an entire year. So you can see the data is starting from 1 to 2% penetration rate. And by the way, by the end of the 2022, we get to as high as about 4 or 5%. Part of it is associated with the company acquiring more data from car manufacturers, but part of it is associated with the gradual increase in the penetration rate. So that's basically two interesting observations for us. The penetration rate is going up slowly but surely. We can actually measure the rate.
Is this something like a percentage of vehicles that are being collected?
Exactly, yeah.
Percentage.
This is percentage of vehicles that are collected in Compass IoT versus the counts of vehicles entering the street and are recorded by loop detectors at the intersection. So we map these two data, fuse these two data sets together, and that rate basically comes out. So you can see I talked about penetration rate and the potential bias. So you can see, for example, different zones in Melbourne metropolitan area are color-coded by the average penetration rate. And you may be kind of familiar with Melbourne. In the center and in the south and in the northwest, we have our rich suburbs. So rich suburbs display higher penetration rates of these vehicles, and poor suburbs, or median and average or low-income suburbs, are basically in the north, northwest, and parts in the east. So it's very clear, if we are making any decisions for operation, we should be aware of this bias, and we should be aware of the equity issues that may actually raise from this difference in data. And this is a bias that is going to stay with us for the next 10, 15 years, because rich populations will start to change their car faster and get that technology faster, and they will get better representation if you're counting them using this technology. The other interesting observation that we made was counts at the intersection. For example, this is one particular intersection, and we looked at the data from an entire month. What's really interesting here is some of these turns are actually forbidden. For example, the right turn here, as you can see in the right bottom figure and the left bottom figure, right turns are forbidden, but we have, for example, a number of vehicles that are making those turns. The rest of the table is nothing really new because we have these counts from loop detectors. What's more interesting than this is the speed of these vehicles, because the detectors at the intersection count the number of vehicles entering the different turns, but we don't count or we don't measure the speeds. What's really interesting is, for example, these speed profiles and speed clustering for the vehicles. So you can see 3 clusters, and this is typical in many intersections that we studied. For example, we observe like three major clusters. Look at the blue cluster, for example. The blue cluster is a case where vehicles are inching forward to the intersection, and as soon as they pass the intersection, they speed up. The red cluster is when there's not a lot of queue, vehicles come to a stop, and then they speed up as well. The green cluster is something that we don't know much about. That's when the intersection is not the bottleneck. There's a bottleneck downstream for the green cluster. That's when the vehicles, with any speed, they get to intersection, but even when they release from the intersection, they cannot speed up. Something going on downstream of that intersection. This is a very unique information. We don't really measure this by any other technology. That's basically the information that can tell me, excuse me, as a modeler, this information tells me if the green cluster is very large for this intersection in this particular direction, then I probably better utilize my green time in another direction. Because the more I release in the green direction, they're going to get stuck in the downstream. So I may use the time at the intersection. For example, if this is north to south, I use that time for east-west direction, for public transport, for pedestrians, and not allocate much to green, because even if I release them to green, they would get stuck downstream either way. So that's an interesting insight, which is very important from operational at the network level and at the corridor level. But in addition to this, I'll talk a little bit more in the next section about the safety implications of the speed data. So going back to the question about penetration rate, the task of fusing these two data sets is a very challenging task, because in Australia, most of our intersections are managed by the SCAT system that is developed in Sydney. And it's a legacy system that has been around for the past 50 years or so. Many different countries use the SCAT system as we speak. The way it works is that there are loop detectors at the intersection, and these are electromagnetic, basically, loops that are under the pavement, and they count the number of vehicles that approach the intersection. So, and this data is available to us. But you can see, for example, for a stretch of road like this is Huddle Street, we basically need to keep record of all different lanes that would come into the road at every intersection and would come out of the road. And there is no kind of existing mapping that we could go and use. So we had to develop methods, smart methods, to identify these loop detector IDs and to map against different directions of the road, to fuse these two data sets. So trying to clarify this a little bit. So the data that is recorded at these loop detectors is the count. How many vehicles are really entering the road? The data that we have is coming from the vehicles directly, and that's the 5% maximum that we have. But we want to know what is the exact number of vehicles that enter, and I'll tell you in a bit what we do with that and how we fuse these two data sets. Any questions so far? Okay. So here is the next step. This is how we fuse these two data sets. So the methodology is borrowed from the literature, but we tested it with our data for the entire year for almost the entire metropolitan network of Melbourne. So imagine for every road, for every day, we have a profile like this. So these are trajectory profiles. On the x-axis, I have time. On y-axis, it's the corridor, it's the space. And you can see vehicles progressing through time and space and making a stop at the delay points and at the intersections before the red lights, for example. These are red lights at different intersections, and they come green and red periodically, as you can see. So these are trajectories that we observe. But there are a lot more vehicles being injected through these trajectories that we don't know. This is very important information because it tells us where do I observe vehicle delays? Where do they accelerate? Where do they decelerate? These are all important from emission perspective, from traffic management perspective, from safety perspective. The most common traffic accident that we observe on our roads is the rear end accident, when vehicles slow down, but the vehicle behind doesn't really know that. If the technology is not there for that vehicle to detect, for example, from the distance and slow down, then we'll have an accident. And that's the most common types of low injury accidents that we have on our roads. So that's part of the value that this data brings to us. Imagine if these traffic signals are operated in a harmonious way, we may be able to produce a green wave or minimize this slowdown and speeds up, as you can see. So the vertical kind of segments are where vehicles are stopped in the traffic congestion. Is this clear? Is this space-time trajectory clear to everyone? All good? Okay. So what we try to do is that from these trajectories, we want to know how do we produce the rest of the trajectory. The body of this text is missing. So what we basically do is we use the traffic flow differential equations, and these equations tell us how vehicles follow one another. How long distance do they keep in front of them? And as soon as the vehicle in front of them speeds up, how long does it take for them to speed up? As soon as it slows down, how long does it take for them to slow down? And that's a function of the distance as well. So simple equations that have been legacy, have been around for past 50 years. They're used in simulation and they're used in research as well. We use those equations and we kind of fuse these two data sets. We inject vehicles here and we follow those equations to produce these delays and to produce these trajectories. What's interesting about these equations, these differential equations, is that they are very network specific. Different cities display different behaviors. Different time of day may actually display different behaviors. People, when they want to go to work in the morning, they are in the rush hour. They want to get there at 8 or at 9. So they're in a rush. In the weekends, they behave differently. Depending on the acceleration power of the engine of the vehicle, we may see different acceleration and deceleration behavior. So some of our vehicles do actually have cruise control, so they would follow automatically. And going forward with autonomous vehicles, we may achieve platoon-based operation, where vehicles communicate with one another and keep their distance as minimum as possible and maximizing the capacity on our roads. All of that can be simply reflected using the differential equation that is used in from traffic flow theory and used in our models. So any questions about that? For example, in Seoul, I noticed that drivers, especially taxi drivers, can be very aggressive and very smart in keeping the distance minimal and really sharp acceleration, really good cars with good power. There are other cities. In New York, I've experienced the same. In Tehran, I experienced the same, where people are really aggressively driving, keep the distance minimal. But I've also lived in Arizona, for example, in a retirement city, where people would keep like 50 meters distance with vehicle in front of them, and they would just take their time. With large vehicles, nothing in the world can worry them. So that's another attitude. So data is necessary for us to understand these behaviors. So if I have enough of these trajectories, I can calibrate the parameters of the model, and I can tell, for example, government, this particular road, for example, it goes to the major business district, for example. In the morning, my population is behaving like this. 80% of my population is driving aggressively. 20% of my population is driving, for example, relaxed, so on and so forth. So for different streets, for different time of day, for different days of week, we may produce that information. And that has a lot of implications, how you can operate the network, how you can, for example, if it's necessary to change the start time of schools, because sometimes you may realize that the start time of school, start time of banks, and start time of government offices, if they are overlapping, then you would have chaos in the CBD. So there are tons of applications associated with this data and can actually be used. But I'll talk about a few of these applications in a bit. Any questions before I move on?
Yeah, well, just a normal way of understanding the vehicle's driver is we normally do some kind of aggregation, like an average value or something like that. But anyway, each country has a specific distribution of the individual data, and probably it's going to be different by country. But anyway, just in a single country or single city, there's a kind of spectrum or distribution of individual data. So sometimes it's very aggressive and sometimes non-aggressive. So did you use that just the one single aggregated value or just the distribution?
Very good point. Yeah, these parameters usually follow a distribution, as you said. Right now, we are just using a single value for every model, for every street, and also for every time of day. But we're hoping our researchers can actually spend more time and discover these distributions, because it's an interesting research question. Sometimes it's actually a very valid modeling question as well. Sometimes we simplify these parameters. For example, in Brisbane, in Australia, we had an issue with modeling. I mean, there were a couple of highways that were built in the hope that the investment would be recovered from the toll. And the toll, for example, was planned, for example, by the economic analysis in advance, considering value of time on average for individuals, how much they're willing to pay to save time. And then it turned out many of those models were garbage because they used a single value for value of time of individuals. They didn't consider the distribution of behavior. They didn't consider variability of this behavior by time of day. And they failed. These were actually turned out to become huge fails for the government because they miscalculated number of people that would use those tunnels and those roads that were supposed to recover its funding from the toll revenue. And people didn't use it because they didn't want to pay. So understanding the behavior is very important, and data is there and requires scientists like us to dig the data and to grab this information, extract this information for economic analysis and for project advisory.
Can I ask
Yes, please.
so if I'm getting this, do I need to? If I'm getting this correctly, are you basically getting the 5% data and then extrapolating it to like a larger population, right? So have you considered any sampling bias from the 5% where you're getting the data from?
Very good question. So the question was, did we notice any bias in extrapolating the 5% to? We know that the bias exists, and we know that majority of these vehicles belong to high salary kind of families and high income individuals, but we still have not gotten to the point to quantify that bias and to take that bias into account. We are just, in our report, the only thing we did, we raised the flag to the government. If they want to use this data, they should be aware of the backlashes and they should be aware of the political kind of issues that may actually be raised afterwards. Because majority of population, the big public force may actually come from middle income and lower income that are probably not represented well in the 5%. I'm hoping I addressed your question, but we didn't really, I mean, this project just started we progressed a lot, but it started in February 2023. So we still have a few more months to go, but it was supposed to be like an elementary analysis, opening up to next projects. Now government knows, for example, what are the most important topics to explore, and now they can kind of invest more, and we can hire sharp PhD students and postdocs to explore those questions.
Well, if I may, questioning in a different way. So it's like how much of bias in 1% and 2% and 5% was something like, was huge in 1% of a simpler way, but 5% was kind of rapidly decreased, the bias decreased. So did you find some kind of clue of it, or?
That's a good question. To be honest, no, we didn't really study the bias. I mean, so far we focused more on the methodology and being able to imagine we have to do this type mapping for the entire network, and we have to develop a software that can do this mapping automatically. Tons of issues, which I kind of didn't really talk about. So it's only at the level of proving the concept and telling, for example, what's really most interesting is this part on a single day on a particular road. When I show this to governments, that did you know that the vehicles that enter this street between these two corridors, they would have to wait for certain amount of time before they can go? Did you know that every vehicle has to come to full stop before they go from this intersection? Did you know that the queue extends from here all the way to the previous intersection on that particular time of day? They didn't, because they only have detectors at the intersection. So they register the presence of the vehicles there, but they don't really have good measures. There are some cameras. Some people actually use cameras, but do we have to go out and install cameras on the entire road to get to that level of information? And in addition to that, all of this, imagine, it has to do it has implications with safety, with emission, and also with efficiency. So this is kind of just peeling the first layer of values here. The question about biases and issues with day-to-day operation is probably one of the questions further down the line. So, yep. So here is just example of this data. Huddle Street again, which is one of the major corridors of arterials in Melbourne that brings people to university and to campus. Simple trajectory of the vehicle from Compass IoT, real data for 15 minutes or so, and then we had to clean it up and merge it with the actual kind of observations from the loop detector. So I'm running out of time. I probably would speed up a little bit, but we may go up until 3 p.m. because we started a little bit late, and then we'll go for a break after that. How about that? Okay, good. So this is actually, again, real data, real observation. What's really valuable and what governments really wants to see is this. We're guessing that this interaction would happen, all this stop and go would happen. But that's based on the single assumption, the single parameter that we assumed. So that's something that actually can be calibrated and can be tested and can be definitely improved. The other topic was intersection management. So intersection management, we are dealing with utilizing this information and improving the signal timing. I'll talk a little bit about the existing technology for intersection management and what can be done with reinforcement learning. So you may all be familiar with pre-timed traffic signals, intersections that are, they know in advance how they operate. For example, if we know the volume of traffic coming to a particular intersection, we may actually go with a certain green time for every direction, and that's basically fixed. More advanced technology is adaptive, when we record the presence of vehicles and we extend the signal timing. So it is basically has its own advantages. It's responding to the demand, and if, for example, if vehicles do not show up, the green time can actually be cut short, and the green time can be allocated to different directions. But it has its issues as well. So the state of the art in this dimension is using machine learning and using reinforcement learning. And one of the main advantages of reinforcement learning is that it's flexible. You can have different objective functions. You can favor different decisions, different policies. It's not always cars, and it's not always presence of cars here that you may want to favor. You can actually extend it to safety consideration. You can extend it to sustainability consideration, and you can extend it to public transport. But with this type of data, I'm jumping on a very important slide. That's one of our papers that got the best paper award, one of the best paper awards at the ITS World Congress, and later on published at in Transportation Research Part C. But that's the methodology, basically. So what I would like to talk about is, with this type information, with this type data, when vehicles, so these are different copies of the road at different time intervals. As you can see, vehicles approach the intersection. After it turns green, they get to pass through. What we usually measure is their presence at the intersection. We don't measure their speed. We don't take into account, for example, the length of this queue, and how many vehicles are entering the link is basically missing. So with this type data, with these trajectory information, we can take into account all of the delay that is exposed, that is imposed on the vehicles. So as soon as the vehicles have to slow down because there's a queue in front of them, or because they see the traffic signal turning red, that information can be reflected into reinforcement learning. So meaning that any reduction in speed can actually be registered and can be utilized. And one of our models is basically dealing with that and showing significant kind of improvements in the operation. So again, the results of this is actually in the paper. If you're interested, just send me an email. I will share with you a copy of the paper. What's more interesting is that we tested it with an actual tram as well. So we have developed in another project a model that can predict number of passengers on tram. So when a tram gets to the stop, depending on where does it come from, where does it go, what is the headway, inter-arrival headway between the tram before it and the tram after it, we predict number of passengers on board. And then when it gets to the intersection, we take all those minutes of all those individuals into account. So it's not just cars, the tram is not registered as one vehicle. It's registered as 50 passengers, and every second that tram is delayed is 50 seconds of 50 passengers. So taking that into account, we can actually improve the operation by something about 10%. And it's a new kind of paradigm. It's a paradigm that takes into account individuals as opposed to vehicles. So some results and some examples there. But again, details should be published for this paper soon. Last cluster of findings is about safety. Safety of operation is actually heavily depends on speed and speed profiles. So if you, for example, the likelihood of a pedestrian to get killed in an accident with cars, if the speed of the vehicle is above 40 kilometers per hour, it's very likely that we will have a serious injury or fatality. But if that speed is below 30 kilometers per hour, it's very unlikely that the individual gets killed. So speed is a very important kind of determinant in safety risk. But that information is missing. That information doesn't exist unless you have cameras that can measure the speed, or you have dual loop detectors that can measure speed. But both of those technologies require investment and require kind of installment at the intersection. This data exists already there, and we can actually utilize it for safety evaluation. So we use VISIM simulation in the back end. Millions of scenarios are being simulated for any kind of demand scenario and for any traffic signal kind of plan. And we evaluate the safety performance at the intersection for vehicle-to-vehicle accidents and for vehicle-to-pedestrian accidents. And using this, we basically kind of extend that to the actual trajectories. So the trajectory profiles that we produce, we consider vehicle-to-vehicle crashes. We consider the angle of the impact and the speed. And from literature, there are models that can tell us, one, the likelihood of crashes, and two, consequence of crashes. So these are two important factors in risk, likelihood and consequence. And we basically bring from simulation models that can help us predict the likelihood of crashes for these trajectories. And we use computer vision to predict these conflict points with the likelihood kind of percentage and a consequence percentage to predict the safety risk. Last but not least, we look at a speed profile at intersection. And this is a speed profile for right turns, for left turns, and for through movements. And this is exactly happening on the sidewalk. If your pedestrians are jaywalking, they're coming in front of different profiles and different values of speeds. And this is very important information when you want to improve the safety for vulnerable road users. So identifying what are the major risks for vulnerable road users and affecting and improving your decisions to operate is actually something that can significantly benefit from this data. We map the data from gyroscopic information against the actual crashes on our road, and we realize that there's really good overlap and there's really good correlation between loss of control that are registered from Compass IoT record versus actual crashes that happened on our roads. Really good goodness of fit with 0.99 R squared. So that basically tells us that this data can actually be used as a good explanatory variable for improvement of safety. So we are working on an array of different models, like how can we calibrate the parameters of traffic flow, how we can improve our fusion, and how we can use computer vision for evaluation of safety. Another data that we have received in this project are the counterpart from bicycles. So these are lights in front of the bicycles that are communicating with the central kind of unit and reporting the GPS locations and speeds and loss of friction events as well. So same for bicycle can actually be used, and we're exploring that. So in a few months' time, we would be sharing the final reports and papers, and would be happy to share with any of you guys if interested. Just reach out to me. So I have other projects that I listed here, but I'm not going to talk about those. These are mainly government-facing projects, practical projects. So they do not really have the novelty dimension. They more have the practical kind of application. In the next lecture, I will talk about a couple of novel models that we have developed, and they're basically from an entirely different domain. They are dealing with mode choice behavior and path choice behavior of the transport users on our road using the data that is collected from fare collection system and from surveys. So thank you very much. Running out of time, so let's take a 15-minute break and then come back again at 3:15. Thank you.